Welcome everyone to the, what is it now, eighth undergraduate seminar series. Our speaker today is Zenobi, and he's going to talk about Legos apparently.
Yes, Lego-ification.
Okay, go ahead.
Okay, hello everybody. My name is Zenobi. Yeah, hi Zenobi. Okay. So for today, I wasn't lying when I said I was kind of going to do like a Lego themed idea, right? So if we look at the shapes I drew over here, let's look at the white outline. We see that these are two flat polygons, this little cross and this square, and imagine the scale is such that they are of equal area. Okay, I wasn't going to draw it like that because I don't want a ruler, but that's what we have here, right? So what I mean by Lego-ification is, can we somehow chop off sections from these shapes, i.e. the triangles here at the side, and say from the other side, from the other shape, we also chop off triangles. But specifically, every time we chop something off, those things we chop off, they have to be congruent. Can we do that in such a way such that the bits that are remaining are congruent enough so that we can, or they are congruent, and we can reshape it to form the new one? Because if you picture this, if we chop off the triangle segments and we lay them on this corresponding side for each of these shapes, we would end up getting this back again. So Lego-ification is my sort of very informal way of stating this word, equidecomposable, which I will be shortening as ED, because my tongue gets twisted the more I say equidecomposable. So that's kind of what we want to look at, right? Because so this is a nice little property. Does it hold for all shapes? At this point in time in the lecture, hopefully you don't know yet. And it'll become apparent soon enough. And then if we look at this, we have a sort of similar definition, but this one is a bit more tricky. What I mean by equicomplementable is sort of a natural inverse of equidecomposable. When I refer to this, what I mean is, can we add congruent polygons so that we can eventually end up with congruent shapes? That's not technically the definition, but if we look here, just for the example, what we could do is we could add, say, this little triangle, this size triangle at each corner. Then we would get this rough, like, sort of colored inside cross shape. And if we do the same for the square, then we would get these added triangles, and then if we trace the outline, these two shapes would be congruent. So technically, that's not what the definition is for equicomplementable. What it would be is, it would be such that, can we add shapes like this such that the resulting two shapes are equidecomposable? I.e., can we build up shapes that can be split into Lego blocks and be reassembled? And that's, if you want to look, here are the formal definitions. Now, if you note the way I define this, so for example here, talk about if P and Q, the two polygons, can be decomposed into congruent polygons, Pi, Pn, P1 all the way to Pn, and Qi, Q1 all the way to Qn, where each of these are congruent with the corresponding same indices. Just for clarity, when I say decomposed, what I mean is we split this into, because everything is set theory, we talk about a polygon. Yeah, we talk about a polygon as a set numbers, or coordinates or items, and then from there we can say, okay, well, if we can say we decomposed it, if the union of all of these give us the original shape and they have mutually disjoint interiors. And that concept as well applies here, where I'm formalizing this. I say, can we find polyhedra P1 all the way to Pn, Q1 all the way to Qn, such that they, for each index, they are congruent, and that we have that the unions of themselves and the original one, these two shapes, end up being equidecomposable. And especially, again, these have to have mutually disjoint interiors.
Is all this in R2?
This is an R2, but these definitions are actually general. The way I've presented them, I've specifically said polygons, but this could be any n-dimensional polygon, which is what I'm going to get to in a second. Because interesting enough, we have that Bolyai and Gerwin. I'm probably butchering their pronunciations. I'm so sorry. They showed that for any two polygons specifically, now this is in 2D, P and Q, that they are both equicomplementable and equidecomposable if and only if they have the same area, which seems like a pretty strong statement, because then we get these nice properties immediately if they're the same area. Well, note this has to be a polygon, and polygon, loosely speaking, a shape with straight lines and edges, no round lines or curved lines or anything like that. So the question is, and that's what we're going to be tackling for the rest of the lecture, does this idea generalize to n dimensions, or at the very least, can we find something for 3 dimensions of similar stature? And there's another reason. So, I mean, this should be reason enough for any self-respecting pure mathematician to look at this problem, because, does it generalize? But there's actually another reason that I believe Gauss illuminated, that if we can find 2 tetrahedra, right? So tetrahedron is a pyramidal structure, like it has a base and all the some base, and these sides all the way go up to 1 vertex. If we can find, right, that for some reason all pyramidal structures, or this is not, no, I just violated the one law I laid out. If we can find that between any 2 tetrahedra with the same altitude, that is a perpendicular height from the base, and with the same base area, if we can find that they are equidecomposable, then this would provide and I quote the book here, it's elementary proof of Euclid's theorem that states that all pyramids with the same bases and the same height has equal volume. And this would be interesting because the proof, if I'm not mistaken, involves using analysis techniques where we're, like, specifically the method of exhaustion, where we kind of use infinite math, analysis techniques to show that these two, that if that a pyramid with the same area base and the same altitude must have the same volume. But if we could do this in a sort of very geometric manner, where we don't have to involve this infinities, then that would be very interesting. So that actually led David Hilbert to, and I always forget the place's name, in 1990, no, not 1990, in the 1900 on the dot. Where is the rag? Here it is. David Hilbert proposed this statement effectively as like one of with 23 open problems to be solved, and it was stating it more formally. Show that there are tetrahedra that are either not equicomplementable or not equidecomposable. This is the problem he posed, because that's, and in lieu of what I just said, that's effectively what he's looking for. He's looking, by the way he stated it, you could see Hilbert suspected that there would be some sort of tetrahedrons that weren't equidecomposable, and hence Gauss's little elementary proof would not really have would not work. But just to something interesting, and that's before we head out to the rest, I want to just mention that if we look at the definitions of equidecomposability and equicomplementability, we see that suppose we have some two shapes that are equidecomposable. If we have that, then we can make two congruent shapes by just adding like a little square here. These two new shapes would then be equidecomposable because we could effectively just cut off these congruent squares, and then we can just cut off all the other ones we already did, and then these two would by definition be equicomplementable, right? So from this we kind of see this important notion that equidecomposability implies equicomplementability. So effectively, all that we're looking for if we want to answer Hilbert's problem is we want to find a tetrahedron such that it is not equicomplementable. Does that necessarily imply it's not equidecomposable? Yeah. Everyone good?
There's something missing there. The way it's so if you compare it with what's on the right, you've got if you compare it with what's on the right, you've got a relationship of area. Are you assuming some relationship of volume?
Oh, not necessarily. No, this is just an interesting result I wanted to show that shows that we can. There's a certain class of polygons that we can always find to be equidecomposable and equicomplementable. In this, I'm not stating anything about the volumes. Oh wait. Oh yeah. Sorry. Yeah. Oh yeah. I missed. Yeah. Okay. Sorry. Thank you. Sorry, I missed that. Thank you, Prof. It is that they have to have the same base area and altitude. Thank you. Yes, that is a necessary part of the question. Cool. So this is where one of Hilbert's students actually came into play. A chap with the name Max Dehn. And he derived a kind of test criterion to see if something was equidecomposable or not. Well, just to see if it's not equidecomposable. To see where this is going, I do have to introduce quite a few notions, so bear with me. We start from here. Firstly, I want to define the notion of what we call a dihedral angle. Right. So if we looked at the polyhedra I just erased from the board, we see that so that all the edges of the polyhedra, let's just look at the cube because cubes are nice. So if we look at the cube, what we see that at some particular edge, let's say this one. Let me do it in orange because it looks pretty. This particular edge. We'll see that this edge, kind of by the way polyhedrons work, corresponds to two faces, which are in essence just subsets of planes, intersecting at some line. So that's what forms the edge. Now we can define the notion of angles between intersecting planes by looking at, say, the angle that their normal vectors make with respect to one another. Right? It's a well-defined concept. We can find the angle between two intersecting planes. So now I want to define this notion, and that's what we call a dihedral angle, is the angle between two intersecting planes of a polygon, of the face, where it's the faces of the polygon, a polyhedra. I define this notion where we have alpha of E, where it denotes the magnitude of the dihedral angle at edge E. Right? Because at every edge, the dihedral angle is uniquely defined because it's in a polygon that just corresponds to only two planes interacting. Note, we don't regard a single vertex as an edge, so otherwise this definition wouldn't make sense. But for example, here's a little nice isolated diagram where I say this is the edge, and then alpha of E would necessarily just be that little angle over there. Cool. Ignore this one now, I'm going down here first. So what we go from here, now the next definition is just a little quick set definition. If I have some polyhedra P, then I denote the set of all its dihedral angles with pi added as m of p. So in the case of a cube, again, it's kind of nice. It's just pi over 2 and pi. And then last, well, not last, but next definition, we have that v of m denotes the set of, and is the glare, can everyone see past the glare? Because I can barely see what I wrote. But it's, okay, cool. Nice not having me not seeing what I wrote as not my fault. This is basically, putting it in words, is the set of all linear combinations of the set M, but where the scalars we use are the rational numbers, right? So this is rational linear combinations of sets. So the letter M here denotes that we're probably going to be using some of these sets in that set. Yeah. And then one small little sub definition left, and then I'm going to write the big definition here. What we have is we also have the concept of a Q-linear function, which is a function from some set of numbers. As you see, we're only going to be using sets of this form from a set to the rational numbers, such that it acts like a linear function that we're used to, but the scalars we extract are specifically rational numbers. So m1 and m2 could be any real numbers, but we can't extract them from the function. Specifically, we can only extract the q's, the rational numbers.
Will m always be finite?
Yes, or m in this mp, or that specific, or this in this definition that we're talking about.
The latter.
Not necessarily,
okay,
but
if it's not finite, by linear combinations, do you mean that almost all of the scalars are zero?
Okay, well, I didn't, to be fair, I didn't bother defining it because we're only going to be using finite m's in this case. Yeah. Cool. So now that we have all this in place, we're finally at a position where we can define what is called the Dehn invariant. And I'm going to put in brackets here with respect to P and F. So if we have, say, if we have some F, which is Q linear, as described above, where F is from a function of the form as follows, where P is any polyhedra, right? So now we map our F as a function that maps from MP, so it'll say Q linear onto Q. If we have this, then we can define, oh, and specifically, not going to forget it again, is that this F also must satisfy that F of pi is 0. We have this, then the Dehn invariant will be defined as the sum, and this is loose notation, so please forgive me. This is where we sum over all the edges of a part of this particular P polyhedra the following values. Where what this denotes, L of E is the length of edge E, and then alpha of E is, as I've defined above, the dihedral angle. So we sum these little terms across all the edges in polyhedron P, where this little set E of P denotes all the edges of polyhedron P. So this is what's going to be the subject of our study, is the Dehn invariant. It looks very arbitrary in a sense at first glance. When I first read the proof, I was not expecting this to go where it goes. But we can actually show that we can get a very, very nice theorem resulting from this. And to do that, I will write it here. if we have P and Q, polyhedra, as we're expecting them to be by this point, with all their and we denote, say, M as the set of all the dihedral angles of one into union with the dihedral angles of the other. In this case, remember, pi is still added, so it's effectively the set of all the dihedral angles in common for all of them and pi. If we do this, and we get some f that satisfies the Dehn invariant thing, where it's like v from f from v of m onto rational numbers with f of pi equals 0 and fq linear. If we find that, and we find that the Dehn invariants with respect to the same function f are not the same, then P and Q are not equicomplementable. So in effect, we've basically narrowed, if we accept the theorem, just, as is, we've narrowed down our very clever way of reducing the problem to just some number we can calculate. And in the case of, say, a cube, it's almost trivial to calculate depending on what we choose. Now the problem is, do we believe that result? I mean, I do. I don't know. You guys are more than welcome to not at this point, but I will try and convince you otherwise. I'm going to, at first, just to kind of complete the proof and show where the picture is going, I'm going to make a claim. And that claim is that if we have a polyhedron P with a decomposition, a finite decomposition, well, I think decompositions are defined to be finite, so that doesn't really matter. But if you have a decomposition, and again, remember from what I said is that a decomposition, all these have mutually disjoint interiors. If we have that, and we have a function f satisfying these properties, then we have that the Dehn invariant of P is just the same as the sum of all the Dehn invariants of all the decomposing polygons. And this property, as I'm going to show now, is the essential reason this whole argument works, and why Max Dehn's contribution to this is why I find it very, very clever. It's because looking at that, it's not obvious why this would happen, but you find that, and then from there, all the properties of equicomplementability and equidecomposability kind of just fall out, like the hit series. Okay. So the way we could go, and I'm just gonna, this is not gonna be the meat of the argument, but the meat of the argument is gonna be proving this, unfortunately. But it's, what we're going to do is, if we have this, then it kind of follows really quickly the end result. Because if we have, suppose that P and Q are equicomplementable, right? By our result, our definition over here, we can find congruent polygons such that the union of all of them and the original shape yield equidecomposable shapes of the yield equidecomposable polygons. So, well, yeah, specifically. So what we can do is you can say, okay, so we're assuming they're equicomplementable. So that means, in lieu of that definition, we can get our PIs and our QIs such that we have this corresponding shape, P, is equal, P tilde, is equal to P union of this. Well, I'm not going to change this to just PIs because we already have the decomposing thing over there. Oh no, but this is different. This is just a general result. These are not the same P. That's all I'm saying. So we suppose P and Q are equicomplementable, and that we can have them, so we can have that this little shape over here, and this polyhedron over here, they are equidecomposable, right? And what that means is that both of these are equal, since they're equidecomposable, we can get a, and here I'll use the tilde notation because why not? We can get mutually just a decomposition such that all these individual bits, such that all these are congruent. And now this involves a result I will not be explicitly proving because it does take, if you want to do it rigorously, that would also be a whole lecture on its own. But I want to state and just briefly justify that if P and Q are some polyhedra that are congruent, then we have the relation that their Dehn invariance will be the same. And this feels natural because if you think of congruency as just, taking the shape and translating and rotating it, then the dihedral angles will remain unchanged and the lengths will remain unchanged. So the sum must also remain unchanged. I will not be proving that angles remain unchanged under congruence, but please trust me. From that, we can get that, okay, so now, if we look at the Dehn invariant of P, that's going to be the same as the sum of the Dehn invariants of these little guys, right? Because that's by our little claim over here. From this, these are all congruent respectively to these. So we have that we can essentially rewrite this little thing. I'm not going to write the indices of the summation just for time. So we have that. That's just the same again as the Dehn invariant of the big function. But from here, we use this decomposition to write out these and deduce that the Dehn invariants of the total shapes have to be the same. But what we could also do is, how about we try and use the other decomposition? Well, this we got from the equicomplementability. From the equicomplementability, what we could find is that, so the Dehn invariant, sorry, this is supposed to be tilde. The Dehn invariant of P tilde is then the same, well, we already know these two are the same, and just expanding them in terms of this, we can get that the Dehn invariant of P plus the Dehn invariant of Pi, well, let me just write out the sum of the Pi's, that must equal the Dehn invariant of Q plus the sum of the Dehn invariant of the Qi's. Now again, these are all the IPI's and the QI's are all congruent. So what happens? From this inequality, these two summations are the same. So we have that the original shapes as Dehn invariants have to be the same. But that contradicts our assumption that the Dehn invariants must not be the same. So P and Q are not equicomplementable. So if you believe that result, then the theorem follows. Everyone happy with that? Keith. Okay. So, yes. So now we're going to tackle the main course, as I like to say. I don't say that often, don't actually get that impression. But it's going to be proving this guy over here. So this is going to be a bit more cumbersome because we're going to have to, at the fundamental level, unfortunately, there's going to be a lot of reliance on physical intuition with regards to how I'm going to present my argument. Hopefully, will be minimal, but let's try it out and see what happens. So suppose we have a polyhedron. Let's just make it a rectangular prism. It was supposed to be a cube, but it's fine. A rectangular prism, and we have some decomposition of this rectangular prism into 3 polyhedra. Let's call them like so. We have this little cube structure over here, this one over here, and then that larger rectangular prism over there. Let's call them P1, P2, P3. Right, everyone, I hope would agree that this is a decomposition. I'm going to do the cardinal sin of proof by example, but you'll see where the argument generalizes from here. If I kind of just look at the top face for a second, like zoom in on the top, what we could see is we're going to get some shape like this. Right? So what I'm going to do, let's call this face, well, this not face, this edge over here, where you see now I put it here and now I forget where it was. Dr. Kelly. Okay, we call this shape, oh, that doesn't look nice and orange, E, this edge E. So let's take this E and treat it as some particular edge. Let E be any edge on P, or not on P, but as part of all the polyhedra decompositions, because technically this isn't on P, but we'll get to that. So here is our face E, or the edge E. Very similar, those two things. Okay. What I'm going to do is I'm going to kind of partition this E into 2 smaller E's, or edges. Label this little segment over here edge 1, and this is edge 2. Okay. So now what I want to do, so by the way, we defined the Dehn invariance, right? If we look at all the Dehn invariants of any particular polyhedron, it could be one of the decomposing ones, or it could be one of the larger shapes. It's the sum over all the edges of that shape. So let's focus on the particular contribution, say, I'm going to just denote it with like a little parenthesis. Let's just focus on the particular contribution, say, from the Dehn invariance of P1 that corresponds to E. Just that single term. Now that single term, we could write that out as, well, the way we defined it is the length of the edge times f of the dihedral angle of P1 at this edge. Note now I've kind of added this index here where this alpha 1 just denotes that now we're focusing on the dihedral angle specifically for polyhedron P1. And in our case, we could see from this little sketch, it's going to be 90 degrees, but let's keep it as general as we can. Okay. From this, let's see if we can sort of write it in terms of the partitions we've made here. Because if we can partition this and write it out as one big summon, then everything could possibly cancel out in the end. So there's a lot of maybes here, but it comes together in the end, I promise. Okay. So firstly, we can note that this little length, well, that's just the sum of the 2 lengths of these edges, right? So we can start writing using what we call, I don't know if you guys have heard of it, but the distributive law. We can write it out as follows. This is the alpha of 1. Okay. So now we have split it up nicely, but still there's some dependence on the larger edge. Can we somehow get rid of it? Turns out really easily actually. Because if we think of P1 as a polyhedron, which it is, then all the edges, or this dihedral angles on that whole edge E will all be the same no matter at which part we're looking at here. So if we redefine our notion of alpha 1 to just include the angle, just to specifically mention that this angle we input here, this edge we input here, sorry, doesn't need to be the whole edge, just a segment of the edge, then that E I can replace with an E1, and this one I can replace with an E2. Is everyone happy with this slide maneuver? Cool. So this leads us to actually consider a nice property of the Dehn invariant. And that nice property is that if we have some edge that can be segmented in this natural way, then the Dehn invariant's contribution at that point can be split into the contributions of all the individual edges. So just to make this a bit easier to write down eventually, I'm going to just define what I like to call the mass. Specifically, let's call it mass I. Is that how I? No. Mass I? Mass I. Okay. Mass I of some ER that is equal to, if ER is somewhere in the set of all the edges of the if decomposition. Again, this is a little bit loose, just follow my words. If we have that ER is somewhere, lies on some edge of the if polyhedron, then we just denote that by the length of ER times f of the alpha I ER, as we've used to now, or else we just denote it as 0. So the reason I do this little slide trick is because what we could do is this eventually will enable us to just write out the summations quick and clean and combine them. But before we get to just all of that, I want to specifically focus on generalizing this kind of idea and showing where it leads. So suppose for some particular I, how are you doing on time, by the way? Okay, so suppose for some particular I, or specifically some particular pi, let's investigate the summation of all, like suppose we had a longer E, where there were even more decomposing polyhedra on this side. Let's write out the sum over all these smaller edge segments. Actually, I realize now this is not just for any particular. We're going at it in full force now. Let's write out the sum over for some particular E, the sum of all the ERs over all the decomposing polyhedra. What we're going to get is we're going to get that, oh, okay, so this mass element over here, this is going to, what's interesting about that is if we look at the way we've defined it, this length function doesn't really depend on I in any meaningful sense. It just depends on the edge we're looking at. So immediately we can kind of just take it out of the first summation, and this is alpha I of ER, right? But now here we can use the whole notion of Q linearity, because what we have here is now we have a summation of a bunch of s, but it's a Q linear function, right? Which, as we've seen, just pretty much behaves like a linear function. So we can take the summation inwards, and we get this. So this is the summation over all the polyhedra pi, all their dihedral angles summed together. Right, everyone happy with my calculation thus far? And I want to show you a simple property of this, which we can see by further inspecting what that actually means. Suppose this, so these ERs, these segments, all form part of some larger edge, right, which happens to be there. But let's look at a few cases for that. What if this edge turns out to just be one of the edges of P? what's going to happen? This summation is the summand of all the angles of the decomposing polyhedra comprising the total object, which is P. So we imagine that if our notions of decomposition and congruency all match up with our physical intuition, then the sum of all the angles comprising that edge has to be the same as the total angle for P. Right? So this summand becomes, in that case, if E is part of the edges of P, then the summand just becomes alpha of E, where alpha of E denoted the dihedral angle of polyhedron P. But now, okay, that might not be the case, because as I illustrated of this, our idea of like the longest unbroken segment E might as well be on a face. If it's on a face, what will all those angles add up to? They'll add up to 180 degrees, because faces of polyhedra are planes, plane faces. So in that case, E is on a face, then the angles will all add up to pi. And if E is, then what's the last remaining case for the edge really to be in? Is somewhere in the interior of P. And that, again, if we have a straight line in the interior of P and we rotate all around it, it's going to be 360 degrees. So you're going to have 2 pi. Moral of the story is this, and we'll get back to these exact results later, but moral of the story, this little summand doesn't end up depending on ER anymore. It just depends on the length, or on the main little edge we're working with, E. So this only depends on E, but this summation is over ER. So we can take this, f of whatever it might be, out of the summand, and now this is supposed to be ER, sorry. Yeah. And now we have the sum of all the smaller segments that comprise E. So from this, that will just be the length of the larger one. So now we have something that looks quite nice. And here's where the magic starts happening, is we're going to start looking explicitly at the summand. Let's write it out in a way that seems to be useful. And again, I'm going to be playing fast and loose with the notation a little bit. But this sum of all the Dehn invariants, these sums might as well just be written out as the sum over all the polyhedra of the summands of all the edges, those longest, specifically longest unbroken edges we were looking at, that are in P. Again, just follow my words. So we have Mi, and by our notion of how we define mass, this would be the case. And this is why I defined it as a piecewise function that could be 0. Because now we're summing over all the edges, but if this edge doesn't lie on the I polyhedra, then this mass term just goes to 0. So it doesn't change the sum. Then we can decompose this little summand into 2 extra summands. So firstly, note that I can partition this into a sum such that E is in this summand, then refers to the edges E are actually an edge of the bigger polyhedron P, and then the remaining summand is where no, this is not where it's just not that, where it's either a face on the face, or like on the face, such as this, or it's somewhere in the interior over here. Now, distributing this summand in, we can kind of swap, because if we look at how these are defined, these sigmas, if we distribute in this summand, can swap, right? So this edge thing can go on the exterior, and this one can go on the interior. So let me just write that out. And by the property, I think, unfortunately, I erased it now, where if we have that E is all is comprised by this composition, then we have that MIE is equal to the sum of all the smaller masses. We kind of showed that. That's the first thing I showed, but I didn't explicitly highlight it. My apologies. If we have that, then we could write, say, this segment over here as the sum of all. Okay, no, it's fine. E on the edges of P. Again, we're looking at those specifically where it's on the edge length of P. And these are just our two familiar summands of 1 over n. And this one is going to be where we sum over all the comprising segments of this E. But we already reduced this to this. So this is going to be the sum of all the edges of E of the polynomial of the polyhedron's main edges of L of E, the length of the edge, times, and since these are on the edges of the main P, we have that they're alpha of the edge. Oh, but that's by definition the Dehn invariant of P. Fun stuff. Now, what happens with this? If you believe my result, then that should be 0. And why would it be? And I'm just going to, I'll erase the proof. We can keep the final result there. But if I give myself some more space here, this is what I call subsetting the board. And then from here, what we could do is, well, here we only concluded that this is alpha of E because the edges were on the sides. But if they're on a face, say, if they're on a face, then we already noted that that would be f of pi. But by the way we defined f, pi is 0. So this whole segment just goes out, just goes to 0, reduces away. And the same goes for if it's in an interior face, because now it's 2 pi, but this is a q-linear function. So the 2 can be taken out. And then this is still just 0. So we see that the second summand will go to 0, and the first one goes to this. Thus, we have recovered our property and proved this theorem. If you're willing to bear with me for one quick minute, I'll just write it on the board how we then show that all of this is actually useful. Let's draw 2 quick tetrahedrons. So suppose this is tetrahedron where all the side lengths are the same, and they, at this little vertex, all the edges are mutually perpendicular. And let's again look at, say, another tetrahedron where we draw it like this, where these 3 are the same. And this is the horizontal area. This is the So these 2 tetrahedrons, if you want, you can check it. They have the same base area, and they have the same height, u. But this one's, let's call this one P and this one Q. This one's dihedral angles all correspond to either pi over 2, pi because we added pi, and arccos of 1 over root 3. Fantastic numbers, right? And from this, okay, I'll get to that now, but we have this. And then we also have that in this case, this set will just be pi pi over 2, pi over 3, pi over 4. So now we need a function f to use this theorem. So why don't we define f on the union of these two, f on MP, oh, no, I'm just not, whatever. We define f as pi equals 0, as we wanted to, and we define f of r cos 1 over square root of 3, that equals 1. If we define it like this, we can show, substituting it all in here, that this Dehn invariant, all these terms of pi, because f is q-linear, will go to 0, all the terms containing the angles of pi, but the term involving the dihedral angle r cos 1 over root 3, that will be a positive number. All of these terms are positive numbers, so this is non-zero. But this one will be 0, because these are just rational multiples of pi. So these two do not have the same Dehn invariant. So these two are not equal complementable, and therefore not decomposable. So sorry, Gauss, and there we're happy. That's the explanation.